The size of a grounding conductor is determined by the rating of the overcurrent protection device protecting the circuit and not the ampacity of the circuit conductors. To properly size a grounding conductor, it's crucial to understand the relationship between the circuit's overcurrent protection and the requirements outlined in the National Electrical Code, specifically Table 250.122. When upsizing conductors to mitigate voltage drop, the grounding conductor size is not necessarily increased proportionally. The primary factor is the overcurrent device, such as a circuit breaker or fuse, that protects the circuit. This device is designed to interrupt the flow of electricity in the event of a fault, such as a short circuit or ground fault. Table 250.122 in the NEC provides the minimum size requirements for grounding conductors based on the rating of the overcurrent protection device. It dictates the smallest allowable grounding conductor size for various circuit breaker or fuse ratings. Let's consider a scenario where you have a 20 amp circuit with two number 10 current carrying conductors. According to Table 250.122, a number 12 grounding conductor is sufficient for a 20 amp circuit. This means that even if you've increased the size of the current carrying conductors to number 10 to address voltage drop over a distance, the grounding conductor can still be number 12, as long as the overcurrent protection remains at 20 amp. The rationale is that the grounding conductor's role is to provide a low impedance path for fault current back to the source, allowing the overcurrent device to trip quickly and safely. The size of the current carrying conductors doesn't directly impact the grounding conductor size requirement in this context. The overcurrent device is the critical factor in determining the appropriate grounding conductor size. It's important to note that local codes or specific installation requirements may sometimes mandate larger grounding conductors. Always consult with the local authority having jurisdiction to ensure compliance with all applicable regulations. Consider the following steps when determining the appropriate grounding conductor size. Firstly, determine the rating of the overcurrent protection device for the circuit. Secondly, consult NEC Table 250.122 to identify the minimum allowable grounding conductor size for that overcurrent device rating. Thirdly, ensure that the selected grounding conductor meets or exceeds the minimum size requirements specified in the table. If there are any local code requirements that exceed the NEC minimums, adhere to the more stringent requirements. Now, let's examine some common scenarios and how to apply Table 250.122. Assume you have a 15 amp circuit. According to Table 250.122, a number 14 copper grounding conductor is typically sufficient. Assume you have a 30 amp circuit. Table 250.122 would likely require a number 10 copper grounding conductor. Assume you have a 40 amp circuit. A number 10 copper grounding conductor may still be adequate depending on specific conditions and the table. Always verify the requirements. Assume you have a 50 amp circuit. Table 250.122 might necessitate a number 8 copper grounding conductor. Assume you have a 60 amp circuit. Table 250.122 might necessitate a number 8 copper grounding conductor. These examples illustrate how the grounding conductor size is linked directly to the overcurrent protection device's rating. Now, let's address some common misconceptions. A common misconception is that if you increase the size of the current carrying conductors, you must also increase the size of the grounding conductor proportionally. As discussed, this is generally not the case. The grounding conductor size is primarily determined by the overcurrent protection device. Another misconception is that the grounding conductor needs to be sized to handle the full load current of the circuit. The grounding conductor's primary role is to carry fault current, not normal load current. It only conducts current during a fault condition, and its size is chosen to facilitate the quick tripping of the overcurrent device during such an event. Consider a scenario with a long circuit run where voltage drop is a concern. You might choose to upsize the current carrying conductors to minimize voltage drop and ensure that equipment operates efficiently at the end of the circuit. However, if the circuit is protected by a 20 amp breaker, the grounding conductor can still be a number 12, as per Table 250.122. This approach is both safe and compliant with the NEC. Let's delve deeper into the requirements of NEC Table 250.122. The table provides a clear and concise guide for selecting the appropriate grounding conductor size. It lists various overcurrent device ratings and the corresponding minimum grounding conductor sizes. It is crucial to use the correct table for the specific type of grounding system being used. The NEC distinguishes between different types of grounding systems, such as equipment grounding conductors and grounding electrode conductors. Table 250.122 specifically addresses equipment grounding conductors, which are used to connect non-current carrying metal parts of equipment to the grounding system. Grounding electrode conductors, on the other hand, connect the grounding system to the earth. These have different sizing requirements outlined in other sections of the NEC. In addition to Table 250.122, other sections of the NEC may also impact grounding conductor sizing. For example, Section 250.130 outlines requirements for equipment grounding conductor connections. Section 250.134 addresses equipment grounding conductor installation. These sections provide additional guidance on how to properly install and connect grounding conductors to ensure a safe and effective grounding system. It's essential to consult all relevant sections of the NEC when designing and installing electrical systems. Now let's discuss some practical considerations for grounding conductor installation. Grounding conductors must be installed in a manner that ensures their mechanical integrity and electrical continuity. They should be protected from physical damage and corrosion. Proper connections are crucial. Grounding conductors must be securely connected to equipment and to the grounding system using approved methods, such as listed connectors or terminals. Avoid using methods that could compromise the integrity of the connection over time. In some cases, it may be necessary to use supplemental grounding electrodes to improve the effectiveness of the grounding system. Supplemental grounding electrodes can help to reduce ground impedance and provide a more reliable path for fault current. The NEC provides guidance on when and how to install supplemental grounding electrodes. It's important to select the appropriate type and size of grounding electrode for the specific application. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The choice of grounding electrode will depend on factors such as soil conditions and local code requirements. Let's consider a scenario where you are installing a new electrical panel in a building. The NEC requires that the panel be properly grounded to ensure the safety of occupants and equipment. To ground the panel, you would typically install a grounding electrode conductor from the panel to a grounding electrode, such as a ground rod. You would also install equipment grounding conductors from the panel to various pieces of equipment throughout the building. These equipment grounding conductors would connect to the non-current carrying metal parts of the equipment, providing a path for fault current back to the panel. When sizing the grounding electrode conductor, you would refer to Table 250.66 in the NEC. This table provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. When sizing the equipment grounding conductors, you would refer to Table 250.122 as discussed earlier. It's important to carefully follow the requirements of the NEC to ensure that the electrical panel is properly grounded and that the grounding system is safe and effective. Now let's address some common questions related to grounding conductors and voltage drop. Question 1. If I increase the size of the current carrying conductors to reduce voltage drop, do I need to increase the size of the grounding conductor? Answer: no, not necessarily. The grounding conductor size is primarily determined by the overcurrent protection device, not the size of the current carrying conductors. Question 2. Can I use a smaller grounding conductor than what is specified in Table 250.122? Answer: generally no. Table 250.122 provides the minimum size requirements for grounding conductors. You can use a larger grounding conductor if you choose, but you cannot use a smaller one unless specifically permitted by the NEC. Question 3. What if my local code requirements are different from the NEC? Answer. In general, local code requirements take precedence over the NEC. Always consult with the local authority having jurisdiction to ensure compliance with all applicable regulations. Question 4. How do I determine the appropriate size of a grounding electrode conductor? Answer. Refer to Table 250.66 in the NEC. This table provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. Question 5. Can I use aluminum conductors for grounding? Answer. Yes, aluminum conductors can be used for grounding, but they must be sized according to the requirements of the NEC. Table 250.122 provides separate columns for copper and aluminum grounding conductors. It's essential to use the correct column for the type of conductor being used. In summary, grounding conductor sizing is a critical aspect of electrical safety. It's essential to understand the requirements of the NEC, specifically Table 250.122, and to apply them correctly. When upsizing conductors to mitigate voltage drop, the grounding conductor size is not necessarily increased proportionally. The primary factor is the overcurrent protection device protecting the circuit. Always consult with the local authority having jurisdiction to ensure compliance with all applicable regulations. By following these guidelines, you can ensure that your electrical systems are properly grounded and that occupants and equipment are protected from electrical hazards. Furthermore, remember that proper grounding is not only essential for safety, but also for the reliable operation of electrical equipment. A well-designed and properly installed grounding system can help to minimize electrical noise and interference, improving the performance of sensitive electronic devices. In addition to following the NEC guidelines, it's also important to use good workmanship practices when installing grounding conductors. Ensure that all connections are clean, tight, and properly insulated. Avoid creating sharp bends or kinks in the grounding conductors, as this can increase impedance and reduce their effectiveness. Regularly inspect the grounding system to ensure that it is in good condition and that all connections are secure. Over time, connections can loosen due to vibration or corrosion. Periodic inspections can help to identify and correct any problems before they lead to safety hazards or equipment malfunctions. Consider the specific requirements of the equipment being grounded. Some equipment may require special grounding provisions or dedicated grounding conductors. Consult the manufacturer's instructions to ensure that the equipment is properly grounded. Be aware of the potential for corrosion when using dissimilar metals in the grounding system. Corrosion can occur when different metals are in contact with each other in the presence of moisture or electrolytes. This can lead to a loss of grounding continuity and an increased risk of electrical hazards. To prevent corrosion, use compatible metals or use corrosion inhibitors to protect the connections. In areas with high levels of lightning activity, consider installing a lightning protection system. A lightning protection system can help to protect buildings and equipment from damage caused by lightning strikes. The grounding system is an integral part of a lightning protection system, providing a path for lightning current to safely dissipate into the earth. When working with electrical systems, always follow safe work practices. De-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to work on electrical systems, hire a qualified electrician to do the work. Working with electricity can be dangerous, and it's important to take the necessary precautions to protect yourself and others.